In 2001, we started this continuous slope area project. Dan Evans and I were discussing how we could improve the rating or the high flow and the medium flow accuracy of a new gauging station on the lower Baba Kamari. We have crest stage gauges on both sides of the channel. This is the right bank looking over the left bank where Dan is. At that time there was a new sensor that came out. It was a mini troll. Dan's taking the mini troll out of the crest stage gauge in cross section 1. As you can see, he's pulling out the stick, and the mini troll is connected on the stick. Dan, why don't you tell us pretty much how this is set up?
Well, here's the crest stage gauge stick. And what we do is, of course, it operates like a normal crest stage gauge. If there's been a flood, the cork will leave a line on the stick. We can, of course, measure up from the bottom, you have the elevation of the bottom of the stick, and get the peak. The transducer also records the peak, it records the entire flow, and we compare, after we correct this to atmospheric pressure, we compare this to the mark on the stick, and they've been lining up fairly well. The purpose of this was to improve the accuracy of our gauging stations. Some of our gauging stations were not able to go out and make direct measurements where we go out on a bridge or a cableway and lower a current meter into the water and measure the velocity. And so we can't access some of these sites because we can't reach them during the floods.
In Arizona, we have a lot of ephemeral streams, which means they only flow after significant rainfall. These rainfall events produce very flashy flood events that only last for a short time. And a tool we can use to better the accuracy of our stream gauges is called the continuous slope area sensors, or CSA sensors. We use these in sites that we can't get to, are far away, or are really flashy, like I said. And what they can do is they can measure stage at multiple places in a stream reach, and then we can put those values into a computer model which estimates discharge for us over the entire hydrograph or the entire flow event. So we can get multiple discharge measurements throughout the flow while we're not there, which makes things, much easier when these sites are so remote.
I'm Steve Wheely. I'm the surface water specialist in the Arizona Water Science Center. And I've been working with Chris Smith and many others on the continuous slope area gauges. When computing the discharge with the CSA data, the CSA gauges work best for medium and high flows. And you can see here in red, green, and blue the slopes between the stage data. The red is going from X2 to X3, the blue from X1 to X2, and the green is X1 to X3, just an average of the other two. So early on in the flow, the water surfaces are disconnected. You can see a large spread between the stages here. As the flow comes up, the slope converges to this point here, and then they remain fairly continuous until the flow declines to about 600 CFS. So in a case like this, we probably want to make our calculations at and above around 600 CFS.
We knew these slope area reaches were there at our gauging stations because that's how we would rate the gauges after major floods. We'd go out, survey the cross sections, survey the high water marks left by the floods. So we knew that these reaches existed at our gauges. So what we decided was to actually go out there and instrument these reaches with pressure transducers.
When we deploy the CSA sensors or put in a CSA gauge, we put multiple pressure transducers in small, low-profile housings within the stream reach. And inside those mounts, we put small pressure transducers. Here's an example of a pressure transducer that we would use. It's about the size of my hand. This has 40,000 data points, so we collect data every 5 minutes. This can stay out at a site for 4 months and continually be collecting river stage data or eventually discharge data while nobody is at the site. These sensors were deployed in many reaches, both in Maricopa County and Cochise County, Arizona, as an experiment to see how well this method could work using these sensors. And the results from these two studies can be found in two reports. These reports are important in this process because they prove the accuracy and the limitations of using sensors like this to calculate discharge.
In the report, Steve has described the different phenomena that we ran into and has shown that it doesn't affect the quality of the continuous slope area.
Another consideration that we've had is just how critical is it to have the upstream and downstream stage gauges synchronized? How much error can we tolerate? It's turned out to be not much of an issue because the clocks and the pressure transducers have turned out to be extremely accurate, showing little or no drift at all. So as long as they're set up correctly, there hasn't been a problem. In the Baba-Kamari data, we were observing consistently that when putting together rating curves based on CSA data, that we were getting much tighter curves using the upstream stage recorder rather than downstream stage recorders. And here's an example at Centennial Wash. Here's a rating curve using the upstream gauge, which is fairly tight, and the rating curve in red using the downstream gauge is showing a lot more scatter. And it turns out that there's actually a reason for this. It isn't just coincidence. And the reason for this is illustrated in these two plots. This is looking at the fluctuations in the upstream pressure transducer. If there's an upstream tick in the stage, the slope is going to increase, which will increase the computed discharge. So the stage moves up and the discharge moves back towards the rating curve because the computed discharge is increasing too. Whereas if there's an upward tick in the stage of the downstream gauge, the stage goes up, but it's going to reduce the slope, and consequently the computed discharge is going to decrease and move away from the rating curve. So that's a likely explanation for why we're getting smoother rating curves using the upstream gauge.
We had a project in Maricopa County that was for measuring channel change, and that was ideal with this continuous slope area, because when you go out in the field and install these sensors in a slope area reach, you go ahead and do the surveying of the channel. And then after a flow event occurs, you come out again and you survey the same channel again. And so you're recording channel change through time.
My name is Claire Bunch. I'm a hydrologist with the U.S. Geological Survey in Tucson, Arizona. When determining the best location for a CSA gauge, we look for a stable reach. Stable cross-sections are important at CSA gauges to verify that the cross-sectional area that is surveyed after the event is representative of the area during the flow event. In order to document any potential channel change at a CSA gauge, we make sure that we document the condition of the reach upon installation. So we will take numerous photos and video. We also survey the cross-sections to document the channel geometry at the time of installation. After flow events, we go back and we resurvey the cross-sections and also take additional photos and video to document the conditions. We're looking to see if any scour or fill has occurred since the installation or since the previous survey. By documenting whether or not channel change has occurred at our CSA gauges, we'll be able to determine the magnitude of an event that causes any measurable channel change. 9 of our CSA gauge locations are part of a Maricopa County channel change study. These gauges have been in operation for almost 15 years, and at these locations we have not detected any significant channel change. One of the gauges, Vehicle Wash, experienced a 25-year flood during the period of record that we've been monitoring and did not experience significant channel change from that event.
Another consideration is whether or not we're capturing the peak discharge. We've been using typically a 5-minute interval, and we're concerned that we might be, especially with the splashy flows we experience around here, we might be missing the absolute peak. But in looking at the data from the 9 gauges in Maricopa County, we're consistently seeing that even in very flashy flows, the peak discharge is not all that sharp. You can see the stage on the vertical axis. And even though this is a very flashy flow, there's quite a good coverage of the peak here with a 5-minute interval. So we're pretty confident that even with 5-minute interval, we're not missing out much on the peak discharges. In this plot, we can see a sample calculation of the error that we do introduce by using a steady flow equation for unsteady flow. And it turns out that in addition to the rate at which the flow goes up and down, the reach slope is also a factor. And so you can see an example here for a simple trapezoidal channel using 3 different slopes, 0.01, 0.001, and 0.0001. For the steepest slope in blue, you can see that the error on the vertical axis is very small, even with very rapid changes in velocity. Whereas for the very low slope, 0.001, the error can start to get very large, even for mild changes in velocity. In Arizona, we're typically in this region here, a fairly steep slope, so it's not been an issue for us, but if you're working in very low slopes, you'd want to pay attention to this. Here's an example from the Babo Kamari, our initial installation. This was a very significant flow there, reaching almost 10,000 CFS and rising and falling very, very rapidly on the first peak, and then a secondary peak that's a bit milder. And you can see in red the error that we calculated over this hydrograph. And for most of the hydrograph, the error is very, very small and reached a peak of plus or minus 3%, which is something we can live with. Here's a histogram of the errors for that same event. Most of the errors are very, very small, just 0.5%, and then it ranges up to just a very small portion of the hydrograph is up about around 3%.
The other thing that we're doing now is we're using the continuous slope area reaches to actually compute Manning's end value. And what we're doing is we're using the slope area reach, measuring the stage, but we're also measuring direct measurements from either a bridge or a cableway in the same area. So we're actually measuring the discharge directly with our current meters, and then what we're going to do is compute in it instead of discharge. And so for this to be the first time that we can actually measure the end value in a flow, in a runoff event, and we can actually evaluate it for different stages. And so we can have it for the high flow, medium flow, and low flow, and we'll see if the end value changes through the stage. One other development that I'd really like to see occur is the particle tracking. If we can go ahead and do particle tracking at one of the cross sections of the continuous slope area reach, particle tracking will give us the surface velocity in that cross section. And then that sensor will actually give us the area. And with that, we will be able to compute discharge. So with this particle tracking, what you do is you use a video camera that's installed on the bank, and you shoot footage of the actual flow of the water at different stages. Other people that have been working on this continuous slope area to develop it is Wes Heaton. He's in our Tempe office. Wes has done an incredible job over the years. I mean, he's an expert in slope area measurements, and we were very fortunate to have somebody like him involved with this development of this method. The other person that's been really important in this process was Jeff Cordova.
We're out on the Hot Springs Wash trying to find a location for a possible continuous slope area. And right now we're just taking cross sections. So right now I'm looking downstream right here.
And Jeff was instrumental in installing a lot of these reaches, running the equipment and processing the data. So the future is to continue to develop the end verification process, channel change, and improve the accuracy of our gaging stations. And I think that with the people that we have working on this now, I think we'll be able to do that. We appreciate all their work and help.